Okay, hello everyone. Uh, I think for your score, I'm still finishing the grading, so maybe wait for next week. Hopefully, I can finish all the scores. And since Tuesday, uh, we didn't have a class, so I think I will try to finish all the chapters that is required. Uh, so after a while, if we need extra class, I will announce. But if we don't need, then it's okay. Okay, we don't need that extra class. And I think for whenever we finish chapter 14, I think we need to have quiz. Okay, one more quiz after we finish chapter 14. This is we still in the middle part. Okay, so we need to have like a half more to go. So last discussions, we have the discussing the linear approximation in terms of function of two variables, which result in a tangent plane, right? With a plane equation. Actually, after this part, I have some exercises, but I think that exercise I will focus on next week. So suppose that we try this and several exercises that I haven't prepared yet. So I think I will add some exercise more here, and we can discuss this part next week. Okay, just for a few parts, a few representative of these questions that I think suitable for your practice. We can try next week. But now let's move to the next part, which is the chain rule. The chain rule in the function of two variables or more. So let's start to discussing this chain rule. Okay, suppose that according to what we have in the tangent plane and the linear approximations, we have these differentials, and this epsilon, it serves like a gap in between, and if we take the definition of limit, this epsilon will go to 0. Okay, so by definitions. Okay, so let me write just for your reference. So as the delta x, delta y approaching 0, 0, then these two values, the epsilon 1 and epsilon 2, will also approaching 0. And if we write in terms of the delta t, so let's divide this with, so multiply, let me write here, multiply with 1 over delta t. Okay. We can rewrite all of this, becomes this delta z. And still, we still have the epsilon. Okay, now for this part, let the delta t approaching 0, then the delta x, or Maybe I'll just follow the next part. It's the same thing. So if we let the delta t approaching 0, and the delta x, which is the delta x is actually the distance between this and this, is the additional delta t. This also gets to 0, and because the delta is 0, which means they are actually minusing the same value, which is 0. And we say that the g, function g is differentiable, and because of it is differentiable, it is continuous function. And then by similar definition, we can take the delta y approaching 0, which means when we have this and this, so delta x and delta y, they both goes to 0, which means that this is going to be 0 and 0. So we could say that this dz or delta 0 delta t in terms of limit definition, just like regular limit. If you remember the previous definition on derivative, partial derivative using limit, we can make this delta z delta t into our derivative definition using limit when it is approaching 0. So by doing that, we can make this into all of this. Okay. So basically we are taking all the sections, all the components, taking the limit for each one of the delta t. So taking that goes to 0. And then we know that this will be 0 because of our definition here. Then we have this at the end. Okay. So this will be our approach for general partial derivative, especially for function of two variables. So we can write this as usually or simply we can also rewrite instead of f, we can just write with z. Which, if you can see how we write this function, this is actually nice and easy to follow. If you carefully see the goal. Okay? The goal is this is going to be derivative with respect to t of our z. We know that z is function of x and y, right? So basically, we can let some variable, let's say parameter, be now here using of t. So all of this variable will be derived with respect to this variable t. So we are going to make a path. We are going to make a way to make this structure of dz dt. How to get that? Because z having function of x and y, we can have two branches. First is this branch, which is deriving with x. But because of the chain rule, this x needs to be derived also with t. In another path, we have z derived with y, and also this y is derived with t, which is actually, if you see just one component here, if you remember in chapter 10, or maybe in the previous calculus 1, this is just a normal chain rule for a function of one variable. You just only see this part. Okay, or maybe in chapter 10, this is a parametric approach of chain rules, right? But since we include two variables, x and y, we need one more variable to help derive all the components. And that is, t can be any variable. You can name it with any variable you want. Okay? We can change this t. But to make it short, to make it easy to observe, we can just write it as. So basically, we have a function of two variables from z, function of x, y. We have two branches. Now imagine if we have three variables. Perhaps we can have a three vector. But we can have set of combinations of many, many functions. And each function can be set of another function again. So if you write, maybe if we, for example, if we take another approach, this is for one case. So for one case, you can write this, okay? One case, okay? So we can set up a function. Let's say x is function of t, y also function of t, okay? And z is function of xy. So they kind of link up with each other. Z link up with x and y. And each x and y will be linked up to t, right? Which is, you can see from the component that we wrote here. We can have two branches, and each branches will link to the function of t, okay? You can make it simply, if we write in terms of like a tree diagrams, we can start with z. Z has two branches, x, y. And each in xy is a function of t. And every time you have branches like this, you set up with something that we call the Leibniz notation, which signifies that this is a partial. So every branches here will be signifies the Leibniz notations. And if you don't have any branch, which means it's just a normal regular derivative, we can just write d. So this will be dx. And that's how we can nicely arrange the structure of the chain rule easily. And imagine, this is maybe just a regular branching, but according to functions, it can be complex and complicated. But as long as you can follow the path, all the chain rule can be easily arranged if you know the link between each function. Maybe this will start with 3, and maybe this one function which is 1, but the other two will maybe 2 or 3. It can be like that. Or maybe just like this, 3 and then 1, 1, 1 is also another possibility. Okay. So it depends on the case, depends on the function, depends on the variables. Okay, depends on the variables. And then another case, okay, another case. If we have, or maybe let me just give you example first, and then we have another case. Okay. So we have this case. Z is, if we look at the function, we only have two variables, and then this will be another function, function x, or this is a function of t with x and y as our function here, which this is going to be connected to this function. Because we need to find dz dt, which means we need to connect this z with functions with the variable t, which is in this two x and y, right? So according to the case here, then we need to connect the z. We can start with this. Okay, although this is a simple example, but let me just write this to help you to get the diagram and the process. Okay. So of course here we get that dz dt is and basically, what we do here is we need to find first what is the dz dx, and basically this is what we did last week. We are going to derive z with respect to x. So we need to treat y as a constant. So we only focus on x. So it will be 2xy, right? And 3y with power of 4. And then similarly, we can take this okay. And let me write the dx dt here. So dx dt is supposed to be cosine 2t. With the chain rule, it becomes 2 cosine 2t, right? And then dy dt, it is cosine t. It will be negative, right? Sine t. To help out analyze the formulations, we can take the when t equals 0, because this is the question, we need to compute the formulations when t is equal 0. Then we can take the x is sine 0 is 0, and y is cosine 0 is 1. And dx dt will be cosine 0 is 1, so it's 2. And then dy dt is 0. And then we can plug in everything. Or if you want, because we have now x, 0, and 1, we can also plug in into the dz dx or partial zx. Let me take up here, and we can write this will be 0, 1. So this will be 0 plus 3 or 3. Let me just write 3. And this will be 0, right? So finally, dz dt is 3, 2, and plus 0, or 6. Okay, so I'm trying to split up all the components and then finally put that into this equation. You can write up, actually, you can write up all the components into one sentence, long sentence. Okay, I think it's also easy. But this is to show you that basically this is what we have as our goal. What you need to do is you need to compute this, compute all of this when t is equal 0. When t is equal 0. So basically that is the goal. Very typical standard questions for chain rule formulations. You have the function two variables, you have all the components of the links. What you need to do is you need to compute everything, compute the partial, and then plug in t equals 0. Okay. Okay. Any questions first? Any question first? Anyone? Anyone confused about the first part? Okay. Hopefully not. Or sometimes, if the student asks like which one is confused, sometimes because when I was still students, I also when the teacher asked, which one is it? Do you confuse? Sometimes students not sure whether they are confused or not. So they don't know how to ask and they don't know what to answer. So they're in between. Oh, I'm neutral. I don't know and I'm not sure. But I think the more you have questions in your mind, the more you have a driving force to look for the answers. Okay? And I think that is good science. So if you don't understand or if you don't understand something, it's good. It means that you know that you don't understand. The problem is when students, they don't know that they don't understand. Do you get it? Do you get it? If they don't understand, they know, oh, I don't understand this, so I need to know this. But sometimes the level is, I don't know that I don't understand. So he's confused by himself. And it's dangerous, If you keep doing this state, you will not going anywhere. It's dangerous. Either you try something that you need to maybe take some either exercise or try testing yourself with some questions. Sometimes maybe you have a nephew, like small nephew, and maybe they asking you, oh, you are studying engineering, and they ask you something related to science. That is supposed to be easy, but you cannot answer that nephew. Sometimes you will feel, why I cannot answer this kid. Okay, when that happens, and you know that you don't know, then it's a good sign. It's a good sign. It means that you know how to go. You need to build that sense, and you need to build that sense. Okay. Okay. Anyway, let me show you another perspective. Okay, another perspective. So suppose that we have this. Okay. This is another example. Function of two variables z. So it branches into x, y. But x and y is branches into two variables, s and t. Not just one single, but it's also another two variables. So we have all partial. And we have two conditions here that it can be with respect with s or with respect with t. So this means, let me make it here. This means we can start from z. We can branch into x and y according to the functions that we built here, the definitions. And x and y, we can have a branch with s and t. So we can write another branch. So this is branch and branch. And all branch, when you walk through, it's actually the derivative itself. I will just draw one example like that. But actually, the same thing happens here, and here. So they're all. So the line means it's partial. Derivative. If it's branch, it's partial. We write with the Leibniz notation. So since we have two options at the end, either with respect to x or t, that's why we have two formulations. So anyway, so based on what we have here, we can have many possibilities that we can just take in generalized version It can be 2, 3, 4, 5, 6 variables or more that we can have. Okay, so as long as you know how to draw the diagram, okay, the tree diagram. So we can have a general versions which we can develop from x1, x2 until some xn. Okay. Okay, let me give you more examples to give you familiarity in this chain rule. Okay. So suppose that, let me just write here. Z is function of xy. X is function of uv. And y is same. I think the same is not interested. Let me change. How about this is 3 and this will be, let me just write with S, R S T. The questions is determine the so partial derivative with respect to S of Z. So every time we have something like this, we can start off with Z, okay, and then taking 3 branches, X, Y, Z, and every X, Y, and Z, another 3 branches. Well, you don't always need to write this diagram, but this diagram can help you. It can help you. So the more you know how to imagine or visualize this diagram, you can write directly the formulations easily. But if you need to confirm, you want to make sure yourself, you can make this up to make sure that you have the right connection with each function. Okay. So by doing this, we can connect this partial z with partial s, or partial derivative with respect to s of z. Or dou z dou s is basically this is z. We need to connect with s, and s. We have 3 types, right? We can go here and here. We can go here and here. We can go here and oh, I have 2z. That's wrong. I just realized. Let me write this w. It's confusing. Okay, maybe this will be better. Okay. Okay, so w will be our top function. So this will be one path, the second path, and the third path. Okay? So 3 components. So we can write okay, so that's it. That's it. Okay, let me give you some other questions here. Okay, now this is, I think, quite interesting. So here we have u that is having 3 variables, and each one of this, except the x, is having relation with x. So this can be can be written as the partial with respect to x so this is interesting. Okay. So this will be y So before we we continue here, we need to be careful. So whenever we have this, it means that all the partial, we need to compute each one of them, which means that, for example, the dx that we have, then we have connection with y and t. The first stage is we can let this derive with respect to x. Okay. If we take that, so if we derive the let me write here. if we derive with we can actually partially derive with implicit differentiations, like we did in previous example, I think last week. So here, we can let the y as a constant and also z as a constant. So in terms of this becomes y plus if we derive with respect to y, this will be x plus z, and dy dx will be cosine x, and plus this will be with respect to z is just y, the other one will be the constant, and dz dx is just the same e. Okay. And since this is y, this is y, this is z, this is related to x, then we change all into x. We can compare later with the implicit versions. Okay, so let me just write this first. So this will be sine x plus x plus e, and plus sine x, or let me write ex sine x. Now let me explain in the implicit terms that we have. Let me review our calculus one implicit, and let's reflect that. And let's see that it's actually the implicit differentiation. It works like this. It works like this. So let me write another question. Let me write another question. So in calculus 1, if we have y cubed plus y squared this is y is function of x, right? Okay, if we want to find dy dx, we can basically derive this, right? All of this directly. And whenever we derive y, we are going to add dy dx. Okay? So let me write this first. So we can collect everything, and I will move here, and this will be 3y squared plus 2y minus 5, right? If we factorize everything with dy dx. Now, suppose that this is this function. Let's say this is our f. Okay, our f, we can write, it's having a two component xy, and y also have x. So based on the chain rule that we have in the partial derivative, we can process what we have in calculus 1 through the same reasons what we have in the partials. So here becomes the dou f dou x, dou f dou y, and dy dx, which gives you, this is equaling to 0. And based on from that perspective, this will be a negative or equal negative. This is partial x partial y. If you see partial x, if you partially derive, this will be only negative 2x. Partial y is the same here, right? Okay. So we can use the same general formula to write off that this is going to be negative will be 2x over 3y squared calculus 1 partial derivative. Okay. Let me write here that suppose and the conditions that need to be happen is when this equals 0. This is equal 0 from the function itself. When we know that it equals 0, f itself this, we can partially derive and basically we can plug into this part. And through the same reasons of what we did here, we can rewrite the implicit in terms of this. Okay, I don't want you to memorize this. What I want you to do is understand the diagram, because when you understand the diagram, you can get everything, the formula like this easily. So you have a function, and define first what is the variable, how much variable, and how the connections. So when you have that, any question in partial derivative is basically like playing puzzle. Which path you take, and then take that as your component and write the formula. Okay. The implicit case is happen when case like this is happening. Or here, this is also implicit because it's actually x is already here, but it's defined again in another layer. This is also implicit. This is implicit, this is also implicit. But this implicit is more general implicit that happen many times. So basically you are x, the partial of f with respect to x, which is, you have this one, but you have another one here and you do the plus. So you may have two different methods. You can have this diagram, and I think this is more generalized, and it can work with every partial chain rule. Okay, or you can use like a similar with calculus one like this, or in fact in our course, as long as you know which part is the constant one, which part is you can derive, you can also directly build this one. Okay? But sometimes the function can be complicated that you need to define first the diagram. Okay? Maybe let me give you another example, just one more example. Maybe let me make it smaller here. Example here. Suppose that we have this equations. Let's say we have a restrictions is equal 1. If z is function of two variables x, y, questions is what is dou z dou x and dou z dou y. Okay, let's take a break. Okay, let's continue this part. Okay. Now, suppose that. Okay, suppose that. Let's say we have a function f. Is going to be equal to the question itself, which is equal to constant. Okay. So when you have this restriction, equal to any constant, it means that it will work with the implicit. It will work with the implicit formula. Because if we derive this, it will be equal to 0. So we can start to write the diagram if you would like to see the diagram first. So the diagram is f, x, y, z, and z is x and y. So this is the diagram. So we can start to write that the dou z dou x. Okay. Dou z dou x means that we want to make the so if the questions is start with the dou f dou x, we are going to get this path and this path, right? From this dou f dou x, we get this two paths that we need to combine. And the dou dou x is actually apart from this path, apart from the diagram, okay? Apart from the diagram. So we can write the dou f dou x generally, okay? So generally we can write plus okay. So actually it's supposed to be the whole thing is from here, but it would be weird, right? It's like it's the same thing as this one, but we know that we have restrictions on a constant. Then we can write this as a 0, right? So the whole thing will be just equaling to 0. And the dou dou x will be negative. So this will be dou f dou x, which is 2x, right? And this is dou f dou z, which is 2z, or negative x over z. So the same thing with dou z dou y. This will be negative. We just exchange x to y, and everything will be the same. And this will be negative y over z. Let me make it smaller first, this part. Okay, wait for a while. Okay. If you want to directly derive with all the assumptions that we have, we can do that as well. So let's say we have this. Okay, this restrictions. So this one is the first method, okay? Using the tree diagram. The second one, suppose that we are deriving with respect to y, suppose. So when we have this, then the x will be treated as a constant, y is a variable, and z is function of xy, just as mentioning in the questions. So this will be 0 plus 2y plus 2z, and then dz dy. Okay. Same thing with the dou z dou x will be giving you the same results. So it depends on which part or which method you take. It should be consistent. But my suggestion, if the function or the connections to all the relation in the function is too complicated, I think you can take the diagram and safer, and you know the path. But if it is just a normal function, regular function, you can just directly take the implicit. Now we move to the other topic. Okay. So, okay. So again, the overview of the chain rule, I think we can take it next week in the Tuesday class. But I think I need to move on to the new topics first. Okay. So my goal this week actually chain rule and directional derivative. So let's just go through these two topics. Okay. This is some of the example that we can have practice, but I will hold this for next week. Okay. So let's go to what we call as directional derivative. Okay. So before we discuss this topic, let me give you some review. So if z is function of two variables x, y, and we can have definitions based on the limit definitions of partial x at some point, basically this is just using limit definitions in defining the rate of change or the derivative. So both of this represents rate of change, right? Each one of them in terms of x or y directions, okay? Which means it will be parallel to each unit vectors in x-axis and y-axis. So our goal, if you look at the words directional derivative, you know the directions because we are dealing with vectors. But we would like to know if we could compute the rate of change that we can get from our partial derivative. So we can find the rate of change. Let me write here. So we can find rate of change of f of or maybe function of two or more variables in any directions. Okay, now suppose we want to find rate of change of z at some point in direction of unit vector u. Let's say this is the directions. If we take the picture, the direction is this according to the xy plane. So we have A, we have B, and this will be the direction. And suppose that this is the point that we would like to observe. And these points are correlated to our point here in the xy plane. And of course, if we imagine this to be similar to what we have in the previous part. So let's say from the picture, you can see that the distance between P accent and Q accent, which is connecting these directions or the distance, the point of the distance, we can call this as HU or HA, HB. H is a scalar factors. And the distance for each component become HA and HB for X and Y. So we can write this as okay. And now we can write the rate of change with respect to, let's say, H, because this is the one that we observe through the distance. Okay, so the rate of change will be equal to F x0 plus HA, y0 plus HB minus F over H. Okay. And if we take the limit definitions when H is getting closer or getting 0, this will be the limit definition for the rate of change. So if we take a limit as H getting closer or getting to 0, then we obtain rate of change of Z in direction of U. Which is called, this is the directional derivative. Or we can just write, let me put this to here, and everything here will be there. So this will be the directional derivative. Or we take the symbol for directional derivative with B, with subscript U. U is the direction of the vectors, or it's supposed to be unit vector of F at this point. If, of course, the limit stays. Remember, the U is unit vector. It's unit vector. Okay, if we compare this with the definitions that we have before, if the unit vector, if unit vector is equal to only one axis I, which means this is going to be only 1, 0, then this will be, so D1F is equal to partial X only, because the other part of Y is 0. And if unit vector is only j, which means that this is only 0, 1, then this is j and this is I, sorry, not. This is partial y. So basically, this is just a normal partial derivative, which give you the definitions that partial derivative of f with respect to x and y are just special case of directional derivative. Okay, so basically, if we could observe through this connection, they are actually the same. What makes the directional derivative different is they have their own direction in the unit vector. In practicality, of course, the limit will be not practical. In practicality, this means that the directional derivative, if we have this vector u, or unit vector u a e, we are going to have each one of the partial x and y will be multiplied with each component of this vector. Okay. And sometimes and I think I don't need to prove this. I think it's easy to prove. You can try by yourself. If you imagine the vectors supposed to be, let's say, this is u. Let's say this is u, and let's say this is at theta. This is x0, y0. This is, and since you have a cosine and sine, you can have two components, and you can have a projections, right? You can make the directional derivative in terms of theta as well, based on the angle. Okay, so you can also relate to the theta. Another connections of this directional derivative is basically using the gradient vector. Okay. What is the gradient vector? The gradient vector is basically, we have this triangle, inverted triangle, which we call the del. The definition of the del is actually It's like an operator in math. That is basically the operator for partial. So every partial, and depends on how many we have, 2 dimension, 3 dimension, or how many variables. This del will be based on how much variables in our function. For example, if f is variable x and y, then the operator of the gradient vector, this will be the partial x and partial y. Okay. So the del will be the dou x and dou y. Okay. So when we have del f, this will be dou x of f and dou y of f. And basically, the gradient is, we can write the whole thing becomes this. Let me just give you this. Okay, I will rewrite again. So the directional derivative is basically just a multiplication of a product of the del f product with the unit vector. This dot means this is dot product, okay? So this is basically and basically this is just another way to write the direction derivative. They are the same thing. Okay, they are the same thing. So this is same thing, and we can write this as a plus. Okay. So you can start from here and then make it to here, or we can start here and make it here the same. But what we have here is actually the component in the direction derivative is basically 2 components, okay? The partial components and the vector. Okay. Because basically the direction derivative is the partial derivative with a direction. Okay. So that's why you need to have a vectors or the unit vectors to be precise. Okay. So basically, whenever you have we call the gradient vector, and if we know the direction, then the product of those will have a, or we can say that that will be the rate of change of that function with direction of u. Okay. So if let me give you an example. Okay, let me give you an example. Let me give you a really simple example. Let's say fine. And it also works for 3 variables as well, okay? with the same logic and definition. Okay, suppose that we have these questions. The direction is in the directions. And since we deal with the vectors, I hope you have some time to review some part of the vectors, especially the things that I emphasize in the videos that I put in the Moodle. At least they give you definitions, the projections, the dot product, the cross product. Okay. So this is a vector, but remember, in terms of the directional derivative, what we have here, the A and B, is unit vector. Okay? So we need to define the unit vector. Or maybe to make it easy to follow, let me make it not you, but maybe with A. Okay. So the unit vector will be A divided with the magnitude value of A. That's the definition of unit vector. Okay. So this will be equal to. So 4 plus 1 is 9. Square root will be 3. Okay, so I hope you get it why this will be 2 over 3, 1 over 3, and negative 2 over 3. Okay, if you feel okay, then I will just write this. Okay, if you feel confused, just raise your hand. Okay. Okay, so this is the unit vector. And then the next part is finding the partial. So partial x will be 2xy. Partial y will be x squared minus z cubed. Partial z is negative 3y z squared plus 1, right? Then the duf is basically the del f dot du. Okay. So duf at 1, negative 2, 0. Or maybe let me take it one by one. Let me input the numbers. This is 1 and negative 2. This will be negative 4. This will be 1 and 0. This will be 1. Put in negative 2 and 0. And this will be just 1. Right? So dot with these unit vectors, and we get negative 4, 2 over 3, plus 1 over 3, plus negative 2 over 3. So negative 8 plus 1 is negative 7, negative 2, negative 9. This is negative 9 over 3, or negative 3. Okay, let me make it smaller. So this is negative 3. What does this negative 3 means in terms of what we have in directional derivative? So this negative 3 means me write here. F is decreasing 3 units whenever F is going into direction of vector A. Okay, lastly, oh yeah, I think this is, I forgot to make up this. So basically this is the 3 variables which the same logic and proving with these 2 variables, okay, all the same, but this is having 3 variables x, y, z, but all the connections, they are the same, okay. So you could simply say that function of 2 variables and 3 variables, they work so well in directional derivative and the gradient vectors, okay, so they're quite similar. What I want to show you is how to maximize the directional derivative, okay. So directional derivative, based on the definitions, is basically we have the del of f dot u, okay. Since this is a dot product, if you remember the dot product that we have, suppose that we have a dot b, okay. In terms of projections, we can write this as, let's say, suppose that this is a vector, both are vectors. We can write this in terms of the cosine theta, right? Which means that since the unit vector, the length is only 1, then we could write this in terms of the definitions through the dot product. Let me write here that this. Where the theta is angle between the del and unit vector. And since max value of cosine theta is 1, then it happen or occurs at theta is 0, or it means that when the unit vector has the same direction with the del f. Okay. So that's how you get the theorem. The maximum, why we should have the same direction with the del f. They have the same direction. Okay, I think that will be the last part for today's class. Okay, any questions? Okay, we are going to have overview next week, some practice and exercise, and hopefully you will get your result for your midterm. And wait, we'll give you the